So last time we discussed limiting reactants and calculating and identifying the limiting reactant in order to calculate the actual yield of a reaction. So in this case, we're given a sentence describing a reaction between calcium hydroxide and nitric acid, and we're asked to calculate the moles of calcium nitrate formed when 3 moles of calcium hydroxide and 4 moles of nitric acid are mixed. And we're also asked to calculate the moles of remaining reactants. Well, first things first, we need a chemical equation. So would someone like to volunteer for calcium hydroxide? What is the proposed formula for calcium hydroxide? Would someone like to propose that formula in the chat or verbally? What's the formula for calcium hydroxide? So calcium typically adopts a 2+ charge. Hydroxide adopts a -1 charge. So if we cross our charges, that gives us CaOH2. And okay, perfect. So we have the formula for calcium hydroxide. What about nitric acid? Would someone like to propose the formula for nitric acid? What would the formula be for nitric acid, which is derived from nitrate? Would someone like to propose? What was that?
H2NO3. No, HNO3.
Yep, exactly right. So the formula for nitric acid would be HNO3. So for nitric acid, it's derived from nitrate, which is NO3 minus. We cross our charges, and that gives us HNO3. Perfect. Okay, now for our products, water, that's pretty easy, just H2O. What about calcium nitrate? So calcium nitrate. So if we have calcium 2 plus and NO3 minus, and we cross our charges, that gives us CaNO3 2. Okay, perfect. So now we have our equation set up. Is this equation balanced? Is this equation balanced? Do we have the same number of atoms of each element on each side? Clearly not, right? So then, if it's not balanced, let's do an inventory. So we have 1 calcium, 2 oxygens, and 2 hydrogens. We have 1 hydrogen, 1 nitrogen, and 3 oxygens. We have 2 hydrogen and 1 oxygen. And we have 1 calcium, 2 nitrogens, and 6 oxygens. Okay, so let's focus on nitrogen. Let's focus first on nitrogen. So in order for us to have the same number of nitrogen atoms on each side, what coefficient do we need in front of nitric acid?
2.
2, exactly right. So with a coefficient of 2, that gives us 2 hydrogens, 2 nitrogens, and 6 oxygens. Okay, so in total now, we have 4 hydrogens and 8 oxygens. Comparatively, if we look at our hydrogens, we see hydrogens not balanced. So in order to balance hydrogen, what coefficient do we need in order to get 4 hydrogens on each side?
2.
2. Okay, perfect. So now we've completed the task of writing out our balanced chemical equation. Now that we have our balanced chemical equation, we're able to execute and begin calculating and identifying our limiting reactant. So here we're going to use the product method. So in the product method, you write down your moles of starting material. So we have 3 moles of calcium hydroxide and we have 4 moles of nitric acid. That's what we're given in the problem here. Okay, and what we're gonna do is we're gonna go from the moles of calcium hydroxide or the moles of our reactant to the moles of product. So that's our overarching goal in this process. So we're going to go from 3 moles of calcium hydroxide to the moles of product, which is calcium nitrate. Okay, so starting with 3 moles of calcium hydroxide, what is our mole to mole ratio? What is our stoichiometric ratio? So how many moles of calcium nitrate do we have per mole of calcium hydroxide?
1 to 1.
1 to 1, exactly right. Perfect. So then that gives us, for our predicted theoretical yield, 3 moles of calcium nitrate. Now remember, this calculation assumes that all of our calcium hydroxide is actually able to react. As we know, that's not always the case. We're going to repeat this calculation for our nitric acid, and we're going to convert our 4 moles of nitric acid into the moles of calcium nitrate. And remember, in our discussion when we used the sandwich making example, the limiting reactant is not always the reactant with the least number of moles. Okay, so if we have 4 moles of nitric acid, what is our mole to mole ratio? How many moles of calcium nitrate do we make per mole of nitric acid that we consume? It's a 1 to 2 ratio. Exactly right. We get the 1 to 2 ratio from our chemical equation coefficients. And that gives us 2 moles of calcium nitrate predicted. So then, my question to all of you is, which reactant is limiting? Which reactant, when completely consumed, generates the least amount of product? Which reactant is limiting?
HNO3.
Yep, nitric acid is limiting. So this quantity here is our actual yield. And we know that nitric acid is limiting. Now, to calculate the leftover or excess, to calculate the excess calcium nitrate, or sorry, to calculate the excess calcium hydroxide, what we're going to do is we're going to take our initial moles of calcium hydroxide and subtract the moles of calcium hydroxide that reacts. So we take the moles of calcium hydroxide that we start out with minus the amount that we reacted. So we take our moles of calcium nitrate that we make and we use that to figure out how much calcium hydroxide did we use up. And we know that we used up 1 mole of calcium hydroxide for every 1 mole of calcium nitrate. So if we punch this into our calculator, that in turn gives us 1 mole of calcium hydroxide left over. Does that make sense to everyone? Does this series of calculations make sense? Yes, please go ahead.
No, 1 to 2 moles. Is that the one from the calcium, and then the 2 from the HMO?
Yes, so the 1 to 2 ratio is based on the fact that if we look at our chemical equation, we see for calcium nitrate, we have a coefficient of 1, and for nitric acid, we have a coefficient of 2. Does that make sense?
Yes. Thank you.
Perfect. Okay, so now that we've seen an example of a limiting reactant problem where you had to write out the chemical equation, let's test our understanding by dealing with the following problem. So I'm giving you a sentence describing a chemical reaction, and I'd like you to calculate the moles of magnesium chloride formed when 2.5 moles of magnesium metal and 2 moles of aluminum chloride are mixed. And I'd also like you to calculate the moles of the remaining reactants. So this example is almost identical to our previous example, except we have a new chemical equation. So let's get started on this example, and then we'll discuss in about 5 to 6 minutes. As a starting point, I like us as a class to really focus on making sure our chemical equation is written out as a skeletal form, and then we flesh out and ensure that our chemical equation is balanced. Once we have our balanced equation, then we can move forward. Does that make sense to everyone? So let's work on this example over the course of the next 5 to 6 minutes. And I'd like to see some proposed skeletal and balanced equations in the chat. And I already see that students have started to provide us a unbalanced skeletal equation. So let's add that to our list. And they even have the state symbols reasonable. That's really good to see. Okay. So we have a proposed skeletal equation. Now let's try to fill in some coefficients and get this equation balanced. And we have students proposing the following balanced equation coefficients. So I'd like everyone to keep working to try to balance this equation, and then I'd like you to note whether you agree or disagree with this proposed student balanced equation. Is everyone comfortable with using this equation as our balanced equation? Does anyone have an alternative solution? Does anyone have a question on this first stage? This is probably the most critical juncture in terms of completing these problems. Once you have your chemical equation, then you can utilize that chemical equation in a range of calculations. So just to make sure we're on the same page, as I see some pretty strong consensus for our chemical equation, let's just talk about how we got here. So magnesium metal, magnesium, it's a metal, it's an atomic species. Aluminum chloride, so we have aluminum 3 plus, Cl minus, we cross our charges, that gives us AlCl3. Magnesium chloride, we have magnesium 2 plus and Cl minus, we cross our charges, that gives us MgCl2. Aluminum, it's a metal, it's atomic. To balance chlorine, we use the least common multiple method. And so we end up crossing our subscript into the opposite coefficient. That gives us our final balanced equation as follows. So the student proposed balanced chemical equation looked great. And now let's take this balanced equation and let's use it to answer these two questions. So let's take an additional 4 to 5 minutes and let's try to get some responses for these two questions. How much product do we actually make? How much product do we make when our limiting reactant is completely used up? And how much of our excess reactant is left over? So let's keep working on this example and we'll discuss in about another 4 to 5 minutes. And I'd like to see some student responses in order to get a sense of how the class is feeling on this topic.
Professor, how do we know the aluminum chloride is aqueous?
So in general, ionic compounds in water would be aqueous. We don't cover the solubility rules in this class. That was just what was proposed by a student for the state symbol. You'll learn in future classes that in general, metal chlorides outside of a select few sets of metal chlorides are generally quite soluble in water.
Okay, got it. Thank you.
But I'm not going to be testing too heavily on the state symbols in this course, beyond the state symbols of common elements that we learned about in earlier chapters. And that's mainly because if we make a product that is, for example, a gas or a solid or a liquid, that's important to consider in future calculations. So we're already starting to see that students are proposing their predicted yield and predicted amount of magnesium chloride generated. Let's try to get a few more responses in the chat, and any responses where I can see some of the work in terms of the stoichiometric ratio. You can even write out your proposed equation. That would also be valid. We are starting to see a class consensus developing that we generate 2.5 moles of product and magnesium is limiting. Would someone like to share in the chat or using the annotate tool a little bit of their logic? And it's great to see students are sharing in the chat not only their final answer, but the calculation that got them there with the stoichiometric coefficients and the stoichiometric ratio. Okay. So let's talk about this first part where we're asked to identify the limiting reactant. Now remember, we have to do this calculation for each of our reactants. Oops, apologies for that. So we're trying to go from, in the first case, from the moles of magnesium to the moles of magnesium chloride. Okay, so if we have 2.5 moles of magnesium, let's find our stoichiometric ratio. So in this case, our stoichiometric ratio, let's use a different color for that. So how many moles of magnesium chloride do we make per mole of magnesium? What's our stoichiometric ratio? 3 to 3. We get the 3 from each of our stoichiometric coefficients. That gives us, for our first reactant, an expected yield of 2.5 moles of magnesium chloride. Okay. So let's continue on now and let's look at our second reactant, and let's go from the moles of aluminum chloride to the moles of magnesium chloride. Now we're given in the problem for aluminum chloride, we start with 2 moles of aluminum chloride. Okay? And what is our stoichiometric ratio? What is our stoichiometric ratio? How many moles of magnesium chloride do we make per mole of aluminum chloride? 3 to 2. Yep. Okay, so that in turn gives us 3 moles of magnesium chloride expected. So which of these reactants is limiting? Which of these reactants generates the least amount of product?
Magnesium.
Magnesium, exactly right. So we conclude that magnesium is limiting, and this 2.5 moles of magnesium chloride is our actual yield. Does that make sense? Okay, so now that we have the actual yield, I'd like you now, over the course of the next 2 to 3 minutes, to tell me how much excess reactant is remaining. How much aluminum chloride is in excess? how much aluminum chloride is left over. And you're going to need the initial moles of aluminum chloride and the moles of the final product that you make from your limiting reactant. So let's try to set up and complete this next calculation where we're figuring out the amount of excess aluminum chloride. So we'll take about 2 to 3 minutes and then we'll discuss. And I'd like to see some proposed responses in the chat and some proposed setups in the chat. And keep in mind, the excess amount of a reagent is always going to be a positive number. So we're starting to see students proposing a setup in the chat. Let's keep working on this example. Let's try to get some final calculated numbers for the amount of moles of excess aluminum chloride. So we see a pretty reasonable setup in the chat. And keep in mind that you'll always end a reaction with less reactant than you started with. So it's great to see that we have 2 students proposing the same valid setup. So let's talk about this setup and let's explain some key things to keep in mind as you punch things into your calculator. So the excess aluminum chloride, we're going to take our initial moles of reactant. And what we're going to do is we're going to subtract the moles of reactant that we consumed. In order to do that, we're going to take the moles of product that we make from our limiting reactant, and we're going to convert it to the amount of reactant that we consumed. So to do that, we're going to plug in our stoichiometric ratio, and we know for every mole of magnesium chloride that we make, we've used up a certain number of moles of magnesium chloride. Looking at our stoichiometry, we use up 2 moles of aluminum chloride per every 3 moles of magnesium chloride that we make. So punching this into our calculator, we get in turn 0.34 moles of aluminum chloride left over that we can just round to 0.3 moles of aluminum chloride. Does that idea make sense to everyone? Does that idea?
Professor, for rounding, which number we are looking at? We're looking at the 2.5 or?
The 2. The 2.
The 2,
Since it has
okay.
the least number of sig figs, we'll round our final answer to 1 significant figure.
Okay, yes. Thank you.
Does that make sense?
Yes.
Perfect. So, any questions on this example? Any questions on this example?
Go over how you got the 0.3.
Could you repeat that, please?
Can you go over how you got the 0.34?
Yes, yes. Let me show you on the calculator. Okay, so in terms of how you'd set this up in a calculator, so the first thing that you're going to do is exactly as written on the board, you're going to enter a 2. That's your initial moles of aluminum chloride. Then,
You see me on the screen, the calculator?
oh no, I'm just So the way that I've written it out is exactly how you'd punch it in with each of the symbols in your calculator. So you'd enter your initial moles of 2. And then what you'd do is you'd hit the subtraction symbol and then parentheses. And then in the parentheses, you'd multiply your moles of product generated, which is 2.5, times 2 over 3. Then you'd close your parentheses and hit the equal sign. So this quantity in parentheses right here is about 1.66. Are you getting the same numbers when you punch this into your calculator? Did everything go okay when you attempted this calculation and entering this line into your calculator?
Yes.
Perfect. Okay, so let's keep going now. And this is just excess space if we needed it. So let's talk about another alternative method that is known as the ICE method or ICE method. So this is a really useful method in order to calculate the amount of reactant and product left over at the end of a reaction. So let's talk a little bit about how the ICE method works and why it can potentially save you time. So let's look at an example where we're asked to calculate how many grams of iron sulfide can form when 64 grams of hydrosulfuric acid and 180 grams of iron 3 chloride react according to the following chemical equation. Okay, so the main benefit of the ICE method is it allows you to answer these two questions. It allows you to essentially determine 1, the expected mass of product, and 2, it allows you to determine the leftover reactant. So that's the two things that the ICE method is very good at simultaneously calculating. Okay, so how does the ICE method work? Well, first thing that we need to do is we need to calculate the moles of each reactant. So the ICE method is very procedural and it's very easy to check your work. So if we're calculating the moles, we're going to need to calculate the moles of iron 3 chloride. And to do that, we're going to take our 180.0 grams of iron 3 chloride and we're going to divide by the molar mass. Would someone like to volunteer and share the molar mass of iron 3 chloride? What is the molar mass of iron 3 chloride? If we want to calculate the moles of each of our reactants, what are the moles of iron 3 chloride?
162.2.
Yep, exactly right. And we got this just by adding up the mass of each of our component atoms in iron 3 chloride. Okay, so we have 180 divided by 162.2, and that gives us 1.109. We're going to carry through an excess of digits, just so that way we avoid rounding errors. Okay, so we've calculated the moles of iron 3 chloride. Let's calculate the moles of hydrosulfuric acid. I'd use that name because it's aqueous. So we have 64.0 grams of hydrosulfuric acid. And in 1 mole of hydrosulfuric acid, we have how many grams? What's the molar mass of hydrosulfuric acid?
34.086.
Yep, exactly right. So then punching that into our calculator, we get 1.882 moles of hydrosulfuric acid. Does this first step make sense? We're calculating the moles because our chemical equation deals with moles. We have a balanced chemical equation, so we're going to use the moles of each of our reactants in order to calculate the expected yield.
So where did you get the 34.0?
Could you repeat that, please?
Where did you get the 30, is it 34 or 39.0?
34.0. So just like always, we obtain our molar masses by adding the mass of each of our atoms found in our molecule. So for example, the molar mass of hydrosulfuric acid would be 1 gram per mole for hydrogen times 2 hydrogen atoms plus 32 gram per mole for sulfur times 1 sulfur atom. And that gives us 34 gram per mole. Does that make sense? Perfect. So now that we have the initial moles, we're going to write our chemical equation into this ICE table. So we're going to write our exact chemical equation into the ICE table. So we have hydrogen sulfide plus iron 3 chloride leads to iron 3 sulfide and hydrochloric acid. We already have our balanced coefficients, so we don't have to worry too much about that. And these coefficients are going to be really important as we look at completing these calculations. So we're going to fill in our initial moles. So we have 1.1097 moles of iron 3 chloride. And we know that we have 1.882 moles of hydrosulfuric acid. Now, I'd like you to pay a really close attention in this ICE table. You're going to really want to focus on your reaction coefficients. So let's write them in green, just so that way we can see how important that they are. Now, what's so important about these reaction coefficients? Well, the reaction itself, as it proceeds, will proceed by a certain amount of progress that we're going to call X. And as a result, we're going to use up some amount of our reactant based on our reaction coefficient and produce a certain amount of product based on the reactant coefficient of your product. So what you're going to do is for all of your reactants, you're going to put a minus sign. For all of your products, you're going to put a plus sign because we're using up reactant and we're making product. Okay, now what you're going to do is you're going to put in this quantity X. This is going to be our change, the amount of change that's going to happen. And then we're going to take our coefficient and put it in front of our change. So as this reaction proceeds, we're going to use up a certain amount of each of our reactants based on their stoichiometric coefficient. So if hydrosulfuric acid is minus 3x, what would iron chloride be? Would it be minus 1x, 2x, 3x, 4x? What would the coefficient be for iron 3 chloride?
Minus 2x.
Yep, exactly right. Likewise, for products, we are making products as the reaction proceeds, so it'll be a plus sign. And so for iron 3 sulfide will be plus or minus. So what coefficient will we have? Plus 1, plus 2, plus 3, plus 4. It would just be plus x because our coefficient is just 1. Does that make sense?
Yeah.
And
for hydrochloric acid, what would the coefficient be?
6x.
Yep, exactly right. So it would be plus 6x. Okay, so now that we have this part of our ICE table set up, we've done the first step of our setup. Now, what's really important to keep in mind, so I'm going to refill in our ICE table, because we're now going to talk about the next really important part of this section. So let me set up and rewrite our ICE table and allow me to fill in our initial moles. So we're just copying what we've written down previously on our ICE table. One moment. Okay, so we're just copying down what we have previously on our ICE table, and we've already have our change coefficients. Okay, so we have our minus 3x, minus 2x, we have 0 moles of product initially, and we have plus x and plus 6x. Okay, so this is the ICE table as we've established so far. Now let's talk a little bit about how the ICE table works. So what we're going to do is we're going to add together our initial and change columns for each reactant and product. And the real beauty of the ICE table, the real benefit of the ICE table, is that the final moles of reactant at the end of a reaction should be 0 if the reaction went to completion. So, in turn, one reactant will be completely consumed before the others if there's a limiting reactant. So you're going to set the final moles equal to 0 for each reactant, and you're going to end up with an expression that looks like this, where you have your initial amount of moles minus your coefficient times x is equal to 0. And now all we have to do is solve for x. Now, there are two ways of going about this. You can either solve it directly, algebraically, or what we can do, so let's write out our expressions. So our final moles, we're going to enter as 0. At the end of our reaction, we should theoretically get 0 moles of reactant remaining. So we're going to end up with an expression. Oops, one moment. There we go. Where we have our initial moles minus our change coefficient is equal to 0. Okay, so this is our expression for hydrosulfuric acid. So solving for x, we get our initial moles divided by our reaction coefficient, which in this case is 3. So one shortcut in order to calculate this change coefficient x is simply taking the initial moles and dividing by the reaction coefficient. So we have 1.882 divided by 3. That gives us a value of x of 0.627. This is our first value of x. We're now going to look at what happens if we assume that iron 3 chloride is completely consumed. So we have the expression 1. So for iron 3 chloride, we have 1.109 minus 2x is equal to 0. So solving for x, we have 1.109 over 2. We have our initial moles divided by our reaction coefficient. When you're calculating the change coefficient, the reason why it's not -3 is that when you move this 3x term to the other side, the sign changes, to answer that question. Does that make sense? Perfect. So we're solving for X, and the simplest shortcut that you can use is you take your initial moles divided by your reaction coefficient. This tells us the amount of change that occurs as the reaction proceeds as we completely use up each of our reactants. So we take 1.109 divided by 2, and we get a value of X of 0.5545. Now, we're not quite done here, because as we notice, we have two different values of X. So what do we do in that case? Well, there's a nice trick for this. So as we discussed, we can solve for X for each reactant by dividing the initial moles by the reaction coefficient. So for hydrogen sulfide or hydrosulfuric acid, we got a value of X of 0.627. For iron 3 chloride, we got a value of X of 0.5545. Okay. Now, clearly, both of these values of X cannot be true. And so the way to identify the limiting reactant is that the smaller value of X is the limiting reactant. Okay, so at the end of our calculations, at the end of this calculation, which of our reactants is limiting? Which of our reactants has the smallest value of X?
Iron 3 chloride.
Yep, so we're going to put a box around this. So we've figured out from this equation and from this process that iron 3 chloride is limiting. Now you may say, couldn't I just use the product method? Well, now that we know that iron 3 chloride is limiting, we're going to plug in this value of X into all of our final mole expressions. And this is where the ICE table really showcases its utility. Because now that we have an appropriate expression that determines how much change actually occurs in our reaction, we can in turn calculate simultaneously the amount of each reactant and each product remaining. And this is really cool. So we have our initial number of moles. Okay, and we know our change coefficients are based on our reaction coefficients. So we're going to plug in this value of X for each of our change expressions. So we have 3X, and this minus 3X turns into 3 times 0.5545, because we said X is equal to 0.5545. That's what we get from our limiting reactant. Likewise, for iron 3 chloride, we have minus 2X, which would be 2 times 0.5545. For iron 3 sulfide, we have plus X, which is plus 0.5545. And for hydrochloric acid, we have plus 6X, which is plus 6 times 0.5545. So the really cool thing about the ICE method is once you figure out your limiting reactant, once we figured out that iron 3 chloride is limiting, and we figured out its change factor, its factor X, we can plug that into our ICE table, and that in turn allows us to calculate the amount of each reactant and each product at the end of our reaction. So let's break out our calculator now, and let's look at this first calculation. So for hydrosulfuric acid, we have 1.882 minus 3 times 0.5545, and that gives us 0.2185 moles of hydrosulfuric acid remaining. Does that make sense to everyone? Does that make...
Could you say again, how did you find the final mole? What formula we're using?
So we take our initial plus our change. So we take 1.882, which is our initial, minus 3x, which is 3 times x, which is 0.5545. And if we punch that into our calculator, initial minus this change expression, we get 0.2185. Does that make sense?
So you're using the I minus coefficient x equals 0. That's what you're using?
Yes, except rather than 0, we're going to calculate how much reactant is actually left over.
Okay.
So one of these final moles will be 0. The limiting reactant will be completely consumed. But for our excess reactant, we will have a little bit left over. And that's why we've calculated the value of x, to figure out how far does this reaction proceed, and as a result, as our reaction proceeds, how much of our excess reactant remains. Does that make sense?
Yes.
Perfect. And to demonstrate this, and to demonstrate and clearly show that iron 3 chloride is limiting, when we take our initial moles minus 2x, minus 2 times 0.5545, we get 0. So we have 0 moles of iron 3 chloride left over. And what does that tell us about iron 3 chloride if it's completely consumed? What does that tell us?
It's limiting factor, limiting element.
Exactly right. Does that make sense?
Yes.
Perfect. So likewise, we can calculate the amount of product that we make. So we see if we add plus x, 0 plus x gives us 0.5545 moles of iron 3 sulfide generated. And we also make 3.327 moles of hydrochloric acid. And this is where the ICE method is very useful, because it allows us to calculate the final amount of each species in our chemical equation in a single organized table. So I find it's a pretty useful method in order to ensure all of your calculations are organized and that it's very easy for you to check your work. The downside of the ICE method is that it takes a little bit of time. So you can use the product method, you can use this ICE table method. Both methods work. I just want you to have as many tools as you can at your disposal. If you plan on taking more chemistry classes, this method is probably the most useful method in terms of developing skills that you'll use in future courses. Okay, so now that we have the final moles, all we have to do is convert from the moles to the mass. So let's say we wanted to figure out how much iron 3 sulfide we actually make. So to figure out the grams of iron 3 sulfide, we just take the moles of iron 3 sulfide and we convert to the grams of iron 3 sulfide. Okay, so let's showcase that. So if we have 0.5545 moles of iron 3 sulfide, we just need to plug in the molar mass, and that will give us our final mass of iron 3 sulfide. So in this case, our molar mass is 55.85 times 2 plus 32.0 times 3. And that gives us a molar mass for iron 3 sulfide of 207.7. So plugging that in, that gives us a final mass of 115 grams of iron 3 sulfide. So one of the other reasons why I really like the ICE method is that it makes it very easy to separate the mass to mole conversion from the stoichiometric conversions. Since I find when students have to do the product method doing a multi-step conversion, it often can get a little bit tricky to make sure all the numbers are in the right spots and to make sure that no rounding errors have occurred. With the ICE method, you convert to the moles, you do all of your mole to mole conversions in your ICE table, and then once you have your final moles, you convert to the mass of product. Does this idea make sense to everyone? Does this idea make sense? Is there a question that I can address based on the ICE table? So let's summarize the process. Let's summarize the process for this one more time. So starting all the way from the top. How did we deal with this problem? So first and foremost, we looked at our chemical equation and we are given the initial mass of our reactants. We then calculated the moles of each of our reactant using the molar mass. And we can calculate the molar masses from the formulas. Now that we have the moles of each of our reactants, we plug that in to our ICE table. To fill in the change portion of our ICE table, we use our reaction coefficients. For our reactants, we are losing reactants, so we have a negative coefficient. For products, we are making products, so we have a positive coefficient. Now, once we have this initial skeleton for our ICE table, we know that at the end of our reaction, one of our reactants will be completely consumed. So one of our final moles for our reactants will be 0. So we're going to figure out the change coefficient for each of our reactants. And by solving for this change coefficient x, whichever reactant has the smaller value of x, that reactant is limiting. So we solved for the change coefficient by taking our initial moles divided by the reaction coefficient. That gave us 2 values of x. The smaller value of x indicates our limiting reactant. So as we discussed and as we saw, iron 3 chloride had the smaller value of x, so iron 3 chloride was limiting. Now, all we have to do now to calculate the amount of each reactant and product is we take our ICE table and we plug in this value of x for all of our values of x. And when we do that, we take our initial minus our change, which is some coefficient times x. And at the end of our calculations, we'll end up with the amount of each reactant remaining and each of our products that we've made. Does that make sense so far? Does that process make sense? Does that summary make sense so far? Okay, so now that we have the moles, if we want to calculate the mass, what we're going to do, one moment, sorry about that, a small amount of lag on the display. So let me wait for it to settle down so that way we can pan to the right portion of the screen. Okay, so now that we have the moles, of product, okay, we're going to convert to the mass of product or whatever final quantity we want, utilizing the correct conversion factor. So in this case, to go from moles to mass, we have to use our molar mass or molecular mass. So this bottom calculation is my calculation for the molar mass of iron 3 sulfide. So I added up the mass of each of our atoms times the number of atoms. So I calculated the total mass of iron atoms, the total mass of sulfur atoms in iron 3 sulfide, and I got this final molar mass. That's what I plugged in up here. Now, to calculate the mass of iron 3 sulfide, I take the moles times the molar mass. The moles cancel, and I'm left with grams. Does that make sense? Perfect. So does this overall process of using the ICE table and calculating the final mass of product generated, does this process make a little bit more sense to everyone now?
Yes.
Perfect. So what I'm going to do is, and I just want to emphasize, the ICE table is just another tool you can use. But I find that if you practice using that method when you're ever unsure, or if you really want to make sure that all of your work is clearly shown and that you want to be able to clearly check for any mistakes in your calculations, I find making an ICE table or using the ICE method is really helpful. Okay.
Professor, I have a quick question.
Yes.
When you got the answer of 115 grams, how come, what is it that we're looking at too? Because I got 115.169.
Yes, that's a very good question. So do you notice how our initial input for hydrogen sulfide only had 3 sig figs?
Oh, okay.
Yep, and that initial input constrains the amount of sig figs that we can report in our final answer.
Okay, got it. Thank you.
So one thing I do want to show everyone, is this idea that we can also solve this problem using the product method. So let's talk about what happens if we try to use the product method to solve this problem. Okay, so we're given that we start off with 64.0 grams of hydrogen sulfide. Oops, sorry about that. One moment, let me return to the page that we were originally at. When the file size gets large, sometimes the screen sharing experiences a little bit of lag. One moment, let me get us back to the page where we were originally at. Okay, so let's pretend we're now looking at this through the product method. Okay, so we start with 64 grams of hydrogen sulfide and 180 grams of iron 3 chloride. Okay. Okay, so our goal is to go from the grams of hydrogen sulfide to the grams of iron 3 sulfide. And to do that, we're going to go through the moles. Okay, now we've seen each of these conversions done individually in our previous example. So let's show using the product method how we'd complete these conversions. So we start off with 64 grams of hydrogen sulfide. And if we use up all of our hydrogen sulfide, what we're trying to figure out are how many grams of iron 3 sulfide we would generate. So in 1 mole, of hydrogen sulfide, we know that we have 34 grams. Okay, perfect. So we've completed our first conversion. Now, using our chemical equation, we can figure out the moles of product that we'd make. So, how many moles of iron 3 sulfide would we make per mole of hydrogen sulfide that we consume? What is our mole to mole ratio? Keeping in mind and looking at our chemical equation. What is our mole to mole ratio between iron 3 sulfide and hydrogen sulfide?
1 to 3.
1 to 3, exactly right, exactly right. So let's plug that in. Let's plug that in right here. Perfect. Okay, and then we know earlier that our molar mass, the key conversion factor that we needed to go from the moles of iron 3 sulfide to the grams, we know that our molar mass is 207.7 grams per mole of iron 3 sulfide. Okay, so if we punch that into our calculator, this will give us the expected grams of iron 3 sulfide if we completely react all of our hydrogen sulfide. So let's enter that in. So we have 64 over 34 times 1 over 3 times 207.7. And that gives us an expected mass of 130 grams of iron 3 sulfide. Okay, so that's the first part of our product method, but we aren't done. We need to do this exact calculation for each of our reactants, So let's do just that. So we're going to take our grams of iron 3 chloride and convert them into the grams of iron 3 sulfide. So we're going to go from grams to moles of iron 3 chloride to moles of iron 3 sulfide to grams of iron 3 sulfide. Okay, so just like before, if we have 180 grams of iron 3 chloride, we then have to use our molar mass. So we know in 1 mole of iron 3 chloride, punching that into our calculator, we know that we have a molar mass of 162.2 grams. Now for our mole to mole ratio. How many moles of iron 3 sulfide do we produce per mole of iron 3 chloride? And let's look at our chemical equation. What's the mole to mole ratio between our product and our reactant iron 3 chloride? What is our mole to mole ratio?
1 to 2.
1 to 2, exactly right. So we'd plug that in here. Okay, perfect. So now that we have our mole to mole ratio, we can convert to our final mass of product using our molar mass. Okay, so punching this all into our calculator, let's enter this calculation string into our calculator, and let's figure out the final mass of product that we would expect if we used up all of our iron 3 chloride. So you have 180 over 162.2 divided by 2 times 207. And that in turn gives us an expected mass of 114.8 grams. Okay, so my question to you is, which reactant produces the least amount of product? Which reactant is limiting? Which
Iron
reactant?
3 chloride.
Yep. Exactly right. So we can conclude that iron 3 chloride is limiting. So let me make that a little bit clearer. So we can conclude that iron 3 chloride is limiting, and this 114.8 grams is the actual yield of product. Now, this compares very favorably if we looked at the calculation from the ICE method. We expected a yield of 115 grams. So as we notice, do the product method and ICE methods give us the same result? Do the product methods and ICE methods give us the same results?
Yes.
Now, it's really up to you which method you find easier. If you can handle and if you like doing these one-line multi-step conversions for two separate sets, you can use the product method. It'll work perfectly fine. But if you like a little bit more separation between the steps, and if you really like to be able to go back and check your work without having to enter a long line into your calculator, then the ICE method is quite useful. The one place where the product method is a little bit less efficient is if you're trying to calculate the amount of leftover reactant. The ICE method, I find, is a little bit faster. So does everyone see how these two methods are complementary, how they both can be used to solve chemical problems, and they both have their benefits and drawbacks? And really, I want to emphasize whatever method you prefer, that's the method you should use. Does that make sense to everyone?
Yes.
Okay, so let's try to test what we've learned. Let's try to test what we've learned. And let's try to look at the following problem. I'm asking you how many grams of nitrogen monoxide can form when 30 grams of ammonia and 40 grams of oxygen react, according to the following equation. Now, since we're looking at grams of product, we're looking at the expected yield of product. You can use either the ICE method or the product method. I've left below an ICE table for your reference. Either way, both methods that we're utilizing, a first order of business that we'll likely need to deal with is to figure out the moles of each reactant, and in turn to figure out the moles of product expected. So let's get started on this example, and let's try to calculate the expected yield, the expected mass of nitrogen monoxide generated as we react 30 grams of ammonia and 40 grams of oxygen. So let's work on this example for about 5 to 6 minutes, and then we'll discuss. And the first thing that I'd like to see from everyone are some mole calculations, so we can begin to fill out our ICE table and so that we can begin to utilize the product method. So let's first try to figure out the moles of each of our reactants, and don't be shy to share your proposals in the chat. And once we have a reasonable pool of responses in the chat, we'll fill in the first step, which is calculating the moles. Then we'll fill in our ICE table, and it'll allow students some additional time to continue with their calculation. So it's great to see we have two proposed amounts of moles in the chat. So for the moles of ammonia, so to get our moles of ammonia, we're going to take our grams of ammonia and convert it to the moles of ammonia using our molar mass. So if we have 30.0 grams of ammonia, we know in 1 mole of ammonia, we have 17 grams, and that in turn gives us 1.76 moles of ammonia. For our moles of oxygen, we know that we're going to take our 40.0 grams of oxygen and convert it to the moles of oxygen. So
Professor,
yes.
why you call NH3 ammonium? I thought ammonia is NH4.
NH3 is ammonia. Yes, you're correct.
But the NH4 thing, it also called ammonium.
NH4 is called ammonium. So while NH3 is called ammonia. So the ium suffix, just as a side note, refers typically to cation derivatives. So ammonia is the neutral species, while ammonium is the cation. Does that make sense?
Yes, thank you.
Perfect. So to figure out the moles of oxygen, as the class has noted, we take and we use our molar mass of oxygen, which is 32.0 grams. Completing this mass to mole conversion, we get 1.25 moles of oxygen. Now, I've set it up so you have your ICE table right below and ready to go. You can choose not to use the ICE table, or you can choose to use another method, whatever method works for you. But I am going to take the liberty of filling in our initial moles. And then I'd like students to either work on filling in the ICE table or telling me the final moles of product that you'd expect from this reaction. So let's try to use the annotate tool to either fill in this table. You can tell me the final moles of nitrogen monoxide, or if you're using the ICE method, you could tell me your final value of X calculated for your limiting reactant. So there are plenty of methods at your disposal, and I'd really like you to take this time to utilize either the product method or the ICE method, and I'd like you to try to estimate the amount of product generated from this reaction. And for the student annotating, would you be able to share your calculated value of X and show how you calculated X? Just so that way the class and we can discuss and sort of get a sense of your logic. Perfect, perfect. Okay, wonderful. So allow me to share and to reformat what your classmate has shared, as this is a really well written explanation and it showcases everything that we're looking for in the ICE method. So let me repackage and rewrite your classmate's proposal, and that way we can have and continue on using this discussion. So first we fill in each of our coefficients. So we plug in each of our coefficients in front of our change. Next, we arbitrarily assign the final moles as 0. So we estimate X for each of our reactants by taking the initial moles over our coefficient. Okay, so for ammonia, we estimated our value of X to be 1.76 over 4 to be 0.44. For oxygen, our value of X is 1.25 over 5. And that in turn gives us 0.25. Now, regardless of whether or not you like the ICE method, this shortcut for identifying the limiting reactant is really useful. It's really fast. So if all you need to do is figure out the limiting reactant, you take the initial moles over the coefficient, and the smaller value of X is the limiting reactant. So based on this data, which reactant is limiting? Which reactant is limiting?
Oxygen.
Oxygen, exactly right. So we concluded that oxygen is limiting. So what we're going to do is we're going to plug in the value of X for oxygen into each of our, whoops, sorry about that. We're going to plug in the value of X for oxygen in for each of our X's in our ICE expression. Okay, so I'd want us to take a moment and I'd like you to tell me the final moles of product. How much product do we get out from this reaction? How much product do we get out? How many moles of product do we make in this reaction? So taking 4 times 0.25, that gives us 1.00 moles of nitrogen monoxide. And since that's all we care about in this problem, we can then move forward and calculate the amount of grams of nitrogen monoxide. Okay. So to figure out the grams of nitrogen monoxide, we take 1.00 moles of nitrogen monoxide and we use our molar mass, which in this case is 30.0 grams per mole of nitrogen monoxide. And that gives us 30.0 grams of nitrogen monoxide as our final answer. Does this idea make sense to everyone? Does everyone see how we can utilize the ICE method to calculate the moles and mass of product expected? Does that idea make sense? Can I get some confirmation in the chat that everyone's comfortable with this process?
Yes.
Is it making a little bit more sense now? Perfect. I know it's a little bit of a hurdle, but the main benefit of this method is it teaches you a lot of shortcuts you can use that can save you time. Now, one thing I do want to show everyone, is how we would utilize the product method. So let's pretend we're dealing with the product method. So in this case, utilizing the product method, so we have 30 grams of ammonia and 40 grams of oxygen. So we have 30.0 grams of ammonia, and we're going to go to the moles of ammonia, then the moles of nitrogen monoxide, then the grams of nitrogen monoxide. Okay. And we have, 40.0 grams of oxygen. We're going to go to the moles of oxygen, the moles of nitrogen monoxide, and then the grams of nitrogen monoxide. So these are our solution maps for the product method. Now let's execute. So we have 30 grams of ammonia. We have 30 grams of ammonia. We know in 1 mole of ammonia, we have 17.0 grams. Now to plug in our mole to mole ratio. We know, so looking at our equation, how many moles of nitrogen monoxide do we make per mole of ammonia? So going up to our chemical equation, what is our mole to mole ratio between nitrogen monoxide and ammonia?
4:4.
4 to 4, exactly right. So we plug in our mole to mole ratio there. Okay, now we're at moles of nitrogen monoxide. And then finally, we convert to our mass using the molar mass. So we know we have 30.0 grams of nitrogen monoxide per 1 mole of nitrogen monoxide. So let's enter this first calculation in. So we have 30 over 17 times 30, and that gives us an expected yield of 52.9 grams of nitrogen monoxide. Let's repeat this calculation for our other reactant. So if we have 40.0 grams of oxygen, we know in 1 mole of oxygen, we have 32.0 grams. Now, what is our mole to mole ratio? How many moles of nitrogen monoxide do we get out per mole of oxygen? Let's look. What's the mole to mole ratio between nitrogen monoxide and oxygen?
4 to 5.
Yep, 4 to 5, exactly right. Exactly right. So plugging that in. So now that we have this ratio, we're in the moles of nitrogen monoxide, and to convert to grams, we just use our molar mass. So punching this into our calculator, we have 40 over 32 times 4 divided by 5 times 30. And as we see, that gets us out 30.0 grams of nitrogen monoxide. So as we notice, which reactant is limiting? Which reactant is limiting? Which? Oxygen. And why is that? Why is oxygen limiting? What's our rule for identifying the limiting reactant?
The smaller amount product.
Yes, exactly right. The limiting reactant, when consumed, makes the least amount of product. So, as you can see, the product method can also allow you to calculate the expected mass of product at the end of our reaction. So both methods are quite useful. Both methods are actively used. And it's really a matter of preference, which method you find most useful to you. Any questions on this example? So, if not, let's keep going. Let's keep going and working through these examples. And I'd like you now to tackle the following open-ended problem. So we have 50 grams of sodium bromide and 100 grams of silver nitrate are mixed to yield silver bromide and sodium nitrate. And I'm only asking you to do two things in this problem. I'd like you to calculate the mass of silver bromide that we make and to determine the mass of the excess reactant. However, this problem is a little bulkier than it appears because what's the first thing that we have to do? What's the first thing that we have to do before we do anything with this problem? What do we need?
Formula.
The formula, yep, and then we need an equation. So let's try to work over the next 2 to 3 minutes on getting a valid set of formulas and a valid set of equations for this problem.
Professor,
Yes.
for the last example, so I was just doing the amount left over from ammonia.
Yeah.
What I'm getting is like that also gets zero. All is getting used up.
Are you plugging in? So just to make one moment.
I don't know if I'm doing it wrong, but when I wanted just to see how much leftover is from ammonia, I get zero also for that.
Are you using the value of X for oxygen? One moment. Let me pan to the page.
I'm using the 30 gram ammonia minus the amount of product times
And are
4
you using
mole.
the product from the limiting reactant?
Yes, but I'm calculating the leftover of the
So make sure that when you convert this 30 grams of ammonia to moles. Well, okay, let me rephrase this. When you start with the moles of nitrogen monoxide, you need to convert this grams of nitrogen monoxide to moles of nitrogen monoxide, then to moles of ammonia, then to grams of ammonia. So just to showcase that calculation, if you take the grams of nitrogen monoxide and divide by the molar mass, multiply by the mole to mole ratio, and then multiply by the mass of ammonia, you'd get 30 grams of ammonia minus, one moment.
Okay.
Minus 30 grams of nitrogen monoxide times 1 mole over 30 grams times 1 mole of ammonia per 1 mole of nitrogen monoxide times 17 grams per mole. And at the end of this calculation, you'd get 13 grams of ammonia left over. Just as you asked explicitly, how do I calculate the amount of leftover ammonia? Does that make sense?
So you do the 30 gram minus the mole of NO, right? Not
So minus so you're converting the grams of nitrogen monoxide into the grams of ammonia. And to do that, we need to do a mass to mole to mole, and then a second mass to mole conversion. Does that make sense?
I'll look at it, and if I don't have more questions, ask you during the office hours.
We'll be doing an example of this process in this next example.
Okay, sounds good.
And when in doubt, the ICE method is also very efficient for calculating the amount of leftover reactant.
Okay.
So let's take a look at this example and let's work for about 2 to 3 minutes on trying to get a balanced equation in this example. So let's try to get some formulas down for each of our reactants and products, and then let's aim to generate a balanced equation. So don't be shy to share your proposed equation skeleton or proposed formulas or even a proposed balanced equation in the chat or using the annotate tool. And if you have any questions, don't be shy to ask. Okay, so we have students proposing a balanced equation in the chat. So let's talk about our formulas. So for sodium bromide, we have sodium plus and Br minus. We cross our charges, that gives us sodium bromide. So for silver nitrate, we have silver plus and NO3 minus. We cross our charges, that gives us AgNO3. Okay, now for silver bromide, we have Ag plus and Br minus. We cross our charges and that gives us AgBr. And then finally, sodium nitrate, we have Na plus and NO3 minus. We cross our charges and we get NaNO3. Okay, so as written, is this skeletal equation balanced? Is this skeletal equation balanced?
It is balanced.
Perfect. So now that we have our skeletal equation, you may want to, and I'm just going to provide you a little scaffold for this, you may want to fill in and make your own makeshift ice table. And the first thing that you'd need to fill in your ice table, are the amount of moles of each of our reactants. So now that we have our equation established, let's take each of our masses of reactants and convert them into moles. So how many moles of each of our reactants are we starting out with? So let's try to fill in this ice table, and don't be shy to contribute your responses in the chat or verbally. So let's try to calculate the moles of each reactant that we are starting out with. And let's try to share our responses in the chat. So for sodium bromide, we see in the chat that students have proposed the initial moles of sodium bromide. So we know for sodium bromide, in 1 mole of sodium bromide, the molar mass of sodium bromide is equal to 23 plus 79 gram per mole. And that gives us for our moles of sodium bromide, 0.486 moles of sodium bromide. Excellent. For sodium nitrate, we know that in 1 mole of sodium nitrate, we have 23 plus 14 plus 16 times 3. And that in turn gives us 1.18 moles of sodium nitrate.
Professor, is that silver nitrate?
Ah, whoops, sorry about that. Yes, that's exactly. Let me reset that. And then for silver, that's 107. There we go. Perfect. Okay, so we've transcribed out what the students have proposed in the chat, and the calculations look reasonable so far. So now we're ready to begin filling out our ICE table. So we have 0.486 moles of sodium bromide. We have 1.18.
Professor,
Yes.
then the mass, molecular mass of silver nitrate then would be different.
Could you share your calculations? Let me just double check one more time. So for silver nitrate, silver is 107 gram per mole, nitrogen's 14, oxygen is 16 times 3. And that gives you an approximate molar mass of about 169 grams per mole. Is that correct?
Yes, and then divide against 0.588, 589.
Let me check. So we have 100 over 169. Yes. Okay, perfect. And that gives us 0.59 moles of silver nitrate. There we go. Perfect. Thank you for the correction. Ah, I see what was being communicated in the chat. You were talking about the expected yield for sodium nitrate. Okay, okay, perfect. So let's plug in those adjusted values. Okay, so now that we have the initial moles of each of our reactants and products, what would our change coefficients be? What would our change coefficients be looking at our reaction coefficients? What are all of our reaction coefficients?
Minus X.
1, yep. So it would be minus X for our reactants and plus X for our products. So now what I'd like everyone to do is, now that we have the initial moles of each of our reactants and the change coefficients, I would like you to tell me which reactant is limiting and how many moles of product will we make. And this problem is intentionally designed so that it's easy to calculate X pretty quickly.
So sodium bromide is the limiting reactant.
Yep, exactly right. And we see that because if we calculate the value of X for sodium bromide, X is 0.486 over 1, while for silver nitrate, X is equal to 0.59 over 1. As we notice, sodium bromide has the smaller value of X, so sodium bromide is limiting. So then, all we have to do to calculate the amount of product is plug in for X, plug in for X, the value of X for sodium bromide. So we plug in 0.486 for X in each of our columns. And this is where the ICE table method really shines, because it allows you to very efficiently not only calculate the amount of product, but the amount of each reactant left over as well. So in the end, we have 0 moles of sodium bromide remaining. Would someone be able to tell me, in terms of our product, how many moles of silver bromide do we make and how many moles of silver nitrate do we have left over? So what are our final moles for our product and our excess reactant? Let's calculate. Please go ahead. So for silver nitrate left over, we have 0.104 moles of silver nitrate. And for silver bromide, we have 0.486 moles of silver bromide. Perfect. Now that we've obtained this data from the ICE table, all we have to do is complete a simple mass to mole conversion. So then we're going to go from the moles of silver nitrate to the grams. So we have 0.104 moles of silver nitrate. We know that for our molar mass of silver nitrate, let me calculate that again, just so that way. So we have 107 plus 14 plus 16 plus 16 times 3. We have 169 grams per mole of silver nitrate times 0.104. That in turn gives us 17.6 grams of silver nitrate left over. And to figure out the moles of silver bromide product, we take 0.486 moles of silver bromide, and we know that we have 107 plus 79 grams per mole of silver bromide. So punching that into our calculator, we have 107 plus 79 times 0.486, which gives us 90.4 grams of silver bromide. And this is the real payoff for the ICE table method, because as you notice, I find personally that calculating the moles of excess reactant using the ICE method is a little bit easier than compared to the product method. So does this example make sense to everyone? Does everyone see how we used each of the pieces in order to calculate our moles of product, grams of product, moles of excess reactant, and grams of excess reactant? Does this example make sense to everyone?
Yes.
Perfect. So this is a great stopping point for today. This is about as difficult of an example as you're going to get on your exam. This will probably be, you'll at least see 2 to 3 of these types of questions on the exam next week. But if you can do something like this, you're set for the exam. This is about as difficult as I can make the questions. This is a limiting reactant problem where you have to write out the equation. And that's what I'm sort of expecting you to be able to do on the exam and on the homeworks that you'll see for this chapter.
Next week, which day test?
The test will be open the entirety of next week, just like we did for exam 1. The exam will be, when you open it, you'll have a certain amount of time to complete it, but it'll be open the entirety of the week for you to pick what day you'd like to work on the exam.
So Professor, we finish chapter 5 and 6 by next week?
Yes, we'll likely finish chapter 6 on either next Monday or Wednesday. And that's why I have the exam 2 designed so that it's open the entire week until Sunday. So that way you have enough time for you to attend the review session that we're having next week, as well as to spend a little bit of time with the material before you're tested on it.
Okay, so we finish chapter 6, let's say next Wednesday, and then we have until next Sunday to finish it?
Yes, yes. But we'll likely get through most of chapter 6 on this Wednesday. Chapter 6 is a very short chapter.
Short one, okay.
Mm-hmm. In terms of the exam, it doesn't have an explicit time limit, but once you open it, you'll have 1 attempt, and you'll have to have your full first attempt done before the deadline on Sunday.
Professor.
Yes.
Can you help me understand on this last 2 problems, 2 sections that you did on this problem? How did you get the 17.6?
The 17, okay, so perfect. So I took the moles of silver nitrate, which we calculated in this end column here. Does that make sense so far?
Yes.
Then we took our molar mass, which we obtained by adding up the mass of silver, nitrogen, and oxygen. So silver is 107, nitrogen is 14, oxygen is 16, and we have 3 oxygens. That gives us 169 gram per mole. So to go from the moles of silver nitrate to the grams, we take the moles of silver nitrate times the molar mass. And so if we take 0.104 times 169, that gives us 17.6.
Okay, got it.
Does that make sense?
Yeah, same thing with the bottom.
Yes, exactly right.
Okay.
Does that make sense?
Yes.
Perfect. So if there aren't any other questions, we'll be closing out today's session. I have office hours today